Okay, we'll start in a few minutes. Let others also join. I hope I am audible. Okay, I'll share my screen now. Is my screen visible? I think no, it's just now. Is it visible? Okay. All right. Okay, now I'm visible also. All right, great. So very good evening, everyone. Welcome back to the week 3 of the live tutorial session for the course Thermodynamics. So in the previous tutorial, we discussed about the work and heat. So we discussed what is work. We developed the expressions for work for both closed system and open system. Okay. And also we ponder over the few initial concepts on heat as well. Okay. So in continuation to that, we'll start with the new today's topic. I hope you all have uh, watched the lecture videos by the professor and are regular with the assignments as well. Okay, so you can unmute yourself and also speak at any point of time, no issues. If you find any difficulty at any point of time, you can unmute. Also, the week 1 and 2 tutorial are uploaded over my channel as well. And you might have got the links in the sheet, Excel sheet, where all the links and the content of this PDF is available. Okay. So my name is Varnit Kapoor, and today we'll be starting with the week 3 tutorial. All right. So I see two of you have currently joined. Okay. Siddhanti, I remember that you joined in the week 1 also. Can you unmute yourself? Yeah, but you missed the week 2 tutorial.
Yes, sir. I said we are going to examination. That's right.
Okay. University exams, you are saying. All right. Okay.
But I want to do later and make you know.
Okay. Okay. All right. Let's start with the next topic, that is first law of thermodynamics, which is also known as energy conservation law, or you can say it as a Joule's law or a quantitative law. Okay. So these are the 4 names for the first law of thermodynamics. So first thermodynamics, or you can say it's that energy conservation law, or you can say it as Joule's law, or also you can say it as quantitative law. All right. So these are the different names of the first law of thermodynamics. So what does it say? So first law of thermodynamics says that for any closed system, we know what is closed system, what is a cyclic process, open system, everything. For any closed system which is undergoing any cyclic process, then the net heat transfer or net heat interaction is equal to net work interaction when they are expressed in their own units. Okay, so both should be in their own units. You cannot compare in our different unit systems. All right, so I'll write that for a closed system undergoing cyclic process. So in layman terms, we say net heat transfer is equal to net work interaction. Okay, but the proper definition of this is for a closed system undergoing cyclic process, net heat interaction is equal to net work interaction when they are expressed in their own units. So points to keep in this definition is for a closed system which is going under a cyclic process, then you say that net heat interaction is equal to net work interaction when they are expressed in their own units, So net heat interaction is equal to net work interaction. These are very important points. Okay, that means you can write as a cyclic integral because they are inexact differential. We discussed in our first tutorial. The net interaction is equal to net work interaction, and both are path functions, not point functions. That's why inexact differentials, writing in the symbol for this. Okay. Suppose you have a PV curve like this of any cycle, okay, auto cycle or whatever cycle you have in your IC engines, okay, which you will study 1, 2, 3, 4 is a process. 1 to 2, 2 to 3, 3 to 4, and 4 to 1 is your complete cycle. Okay. So how you will write in the terms of 1, 2, 3, 4. So net heat interaction from the process 1, 2 plus process 2-3 plus process 3-4 plus process 4-1 is equal to work done in 1-2 plus work done in 2-3 plus work done in 3-4 plus work done in 4-1. This is your net heat interaction is equal to your net work interaction in a cyclic process when they are expressed in their own units. Points to be noted here is that this equation, let us say this is equation number 1, very important equation for first law of thermodynamics. So this equation is applicable both for reversible as well as irreversible processes because both are in the cyclic, both are valid for cyclic process. Okay, let me write. We know what is reversible, what is irreversible. All these terminologies we have discussed very well in our previous tutorials. Okay, so equation 1 is applicable for both reversible and irreversible process because both are represented for cyclic process. Okay, next, this equation 1, what is the problem with this equation 1 is that it is only applicable for a cyclic process because in the terminology we know that for a cyclic process. Okay, this equation 1 is valid only for a cyclic process but not applicable for a particular process. Suppose you are going in the cycle from 1 to 2. Okay, from 1 to 2 you want to go, then what will be your heat interaction or work interaction if you want to calculate process by process if you want to go. Okay, so this equation is not valid for non-cyclic process. That's an issue. So what is the problem? Equation 1 is it is applicable only for cyclic process not applicable for a single process. Okay, all right, if you want to go suppose from single process means if you want to go from state 1 to state 2, what is net heat interaction or work interactions? Now coming to the consequences of first law of thermodynamics, right? First law of thermodynamics. TD is a short abbreviation for thermodynamics. So heat is a path function. Now we need to prove that. We understood this term in the previous tutorial, but we will prove this thing. The first thing is heat is a path function. Let's prove. So suppose you plot a PV plot. Yeah. Okay. You have state 1 to 2, you are going. Okay. So one way is you go with this path A. Other way is you go by this path B. Sorry. Let's take, first you go from A to B. 1 to A22, then 2 to B21. Suppose if you take like that. Let me do one another way. Okay. So first you went from 1 to A to 2, then you went from 2 to B to 1. Okay. There are two paths. Other way can be if you go from 1 to A to 2 and 2 to C to 1. All right. These are the two paths you have. Three paths you have. A, B, C. Returning two paths, going one path. So the first path is that Q, the heat interaction from 1A2 plus Q2B1 is equal to net work interaction 1A2 plus work 2B1. Okay. So the first cycle 1A2, 2B1. Then next cycle 1A2, 2C1. Next cycle is Q1A2 plus Q2C1 is equal to work 1A2 plus Q2C1. Okay. These are the two equations you have. Subtract both the equations. Let us subtract. So if you subtract it out, what you will have, this term gets cancelled, this term gets cancelled. You are left with only Q2B1 minus Q2C1 is equal to 1 work 2B1 minus, oh sorry, this should be work 2C1. All right. Now if you see, we know that area under the PV graph gives us the work PdV. Okay, we have discussed this. So if you see, work 2B1 represent work 2B1, area under this represents this area. Okay, 2B1. Whereas 2C1 represents this area. Right? I'll draw like this. Okay, just below the blue curve. So if you see, there is a common still region left, which is this one, which is not zero. This area is not zero. So 2B1 minus 2C1 is this zigzag shaded region in blue, which is non-zero. All right. Okay. So this is, all right, this part is non-zero. So that is why heat interaction is also not zero. Therefore, Q2B1 minus Q2C1 is also non-zero. So that's why, therefore, Q2B1 is not equal to Q2C1. So this is not a point function. This is a path function. It depends on the path which you are taking. All right. It depends on the path which you are taking. Here, work 2B1 is not equal to work 2C1, and heat is also not equal. So heat is a path function. We have proved. Hence, proved. All right. Now, second, this was the first. Second scenario for the consequence. Second consequence is energy is a property. Let's understand that. Okay. Energy is a property. So if it's a property, also it's a point function. Okay. All right. So let us say this equation is equation C. Not C, let's say. This equation is equation A. Okay. So energy is a property. So use this equation A. Using equation, that is Q2B1 minus Q2C1 is equal to work 2B1 minus work 2C1. All right. Transpose the work to be 1 on left hand side. So 2B1, both the terms together. Q 2B1 minus work 2B1. You have taken this here and taking this there. All right. Q 2C1 minus work 2C1. So if you see, this whole of the process is equal to some value, It's non-zero, as we know. And that is nothing but a change in the energy from state 1 to state 2. So we can, this is non-zero. We know that from equation A. So this is nothing but equal to change in the energy from 1 to 2. And we can write it as an exact differential. Okay. Point functions are exact differentials. Okay. So energy is a point function. Heat and work are state function, path function, sorry. Okay, it's a, all right. State and path functions we have discussed. So as heat and work are path function, but difference of heat and work is a point function. From this, we can understand that this implies heat and work are path functions, but difference of heat and work is a point function. Okay. So we can write this in the form dq minus dw. This is dq minus dw only. Q minus w is equal to change in energy, dE, del Q minus del W. So you can write del Q is equal to dE plus del W. Okay, very important question. All right, very important. So this energy E in this is a sum of various forms of energy like potential energy, kinetic energy, or internal energy. Okay. So you can write this energy is summation of various forms of energy like kinetic energy, potential energy, internal energy, short forms I'm writing. Okay. So what you can write? dE, that is, dE is nothing but d of kinetic energy plus potential energy plus internal energy U. Okay, U. So kinetic energy and potential energy are macroscopic form of energies. These are macroscopic form. All right. Whereas internal energy is at molecular level. Okay. So all form of energy at microscopic level. Okay. Or you can say it is a inbuilt energy associated with the molecules. Okay. So this is microscopic form. So this is group of molecules. Macroscopic. And microscopic is all form of energy at microscopic level. Or you can say inbuilt energy associated with molecules. All right, clear. So if you ignore the microscopic forms, that is kinetic and potential energy, you can write the change in energy is nothing but change in internal energy by neglecting kinetic energy and potential energy. All right. Okay, very important. So what you can write, the equation, this in the red box, your equation can be del Q is nothing but du plus, okay, someone is trying to join. Okay. Del Q is nothing but du plus del W. Very important equation. Very important equation in perspective of first law of thermodynamics. Okay. Now this del W is can be of two forms. Either it can be a boundary work or it can be a non-boundary work. Okay. Either it can be a boundary work or it can be a non-boundary work. Right? What are the examples of non-boundary work? Like if you have a stirrer or a paddle when it work inside a in a liquid in a closed chamber. Okay. Or electrical work is a non-boundary work, or a shaft work is also non-boundary work. Okay. So I'll write some here like steering work or paddle wheel work. Like if you have a fluid and there is a fan or a paddle inside it. So here it is internal to the boundary. So this is your boundary. Okay. And this work is outside to the boundary. Work from external to the boundary. All right. Or you can say electrical work. So what is happening here? I'll clear that paddle wheel is working on the fluid here. Paddle wheel is working on the fluid, but here the fluid is not changing, crossing the boundaries. Paddle wheel is working on fluid here. Paddle wheel is working on fluid, but fluid is not crossing boundary. All right. So this is your non-boundary work. Other can be electrical work or shaft work. Okay. Now let's come to condition for applying the PDV, which is a PDV work. Okay. When we say that work is equal to PDV, which is a closed system work, we have done that. And negative of VDP is open system work. Conditions for applying PDV work. First, it should cross the boundary. Like in the parallel work, steering work here, the fluid is not crossing the boundary. So it's a non-boundary work. That means for application of PDV work, it should cross the boundary and it should be a closed system. PDV is applicable for closed system. First thing, it should be closed system. Also, it should cross the boundary. That is nothing but boundary work. Also, it should be a reversible process. Why? It should be reversible process because we are taking a reference of maximum efficiencies in our system. So when the process is reversible, we can say that it will achieve a maximum efficiency. Okay, maximum work we can get out of it. All right, it should be reversible process. Then only if these three conditions satisfies, then only you can apply PdV work. Then only you can apply the PdV work. Okay. So we can write the above equation in the right box as del Q is nothing but du plus PdV. Again, very important equation it becomes. Okay. Now, one question also arises in mind of students is that does a closed system will be cyclic always? Is it necessary? So it is not necessary that if you have a box and there is a gas inside it, then there is energy transfer, but it's not a cycle. Energy can be transferred inside the box by any means, but it's not a cycle. So but it's a closed system because it's inside the box. So only energy transfer is happening, mass transfer is not happening. It's a closed system, but it's not a cyclic process. So every closed system doesn't need to be necessarily a cyclic process. Okay. All right. Next, if you see this equation in the red box, it's applicable only for reversible process and closed system as only boundary work is there. This is applicable for only reversible process and closed system as only boundary work is there. All right. Okay. Pretty much clear. Very important term. Whenever we are going to apply, this condition should be always been in your mind why you are applying and when wonder what condition you are applying. Now the next consequence is that third, energy of isolated system is constant or change in energy is zero. Energy of isolated system is constant or change, or you can say change in energy is equal to zero for an isolated system. Okay. Insulated system means heat interaction is zero. Net heat interaction is zero. But isolated system means net energy interaction is zero. DE is zero. Okay. So that is del Q is nothing but DE plus del W. We know that. So in an isolated system, this is zero for an isolated system. Okay. So you can say then you're for an isolated system, I'm saying I'm very particular about that. And this is energy at microscopic plus macroscopic level. All right. So energy in final, since energy final minus, or let me write like this. Since D is equal to zero, this implies energy final is equal to energy initial. Okay. In a short way, you can say that insulated system. Insulated means del Q is equal to zero, and isolated means dE equal to 0. Okay. All right. Clear. The fourth point is, what is PMM1, perpetual motion machine 1? Okay. As per first law of thermodynamics, it says that it is impossible to construct a PMM1 kind of machine because it violates the first law of thermodynamics. Because it is impossible to construct a device which produces work continuously without containing any other form of energy. Any other form of energy. So it is not possible. PMM1 impossible because it violates first law of thermodynamics. First law TD for short, thermodynamics. It states that it is impossible to construct a device which produces work continuously without consuming any other form of energy. Right? That means so net heat interaction from the first law is net work interaction. Okay, it's not possible that net heat interaction is equal to net work interaction. So without consuming, if this is 0, then this will also be 0. It's not possible that this is 0 and this is non-zero. Okay, so if it happens, then it's a PMM kind of machine, which is impossible to construct. Okay, and it will violate the first law of thermodynamics. Okay, so suppose you have a machine, you are producing work out of it, but you are not giving any heat into that system. So heat is 0. It's not possible. Even for running a vehicle, if you say, short example, you want a fuel to supply so that it converts into a chemical energy is there. That energy is used to create a shaft work in the form of output so that your vehicle runs. Okay. It's not possible for any machine to produce a work continuously without consuming any form of energy. Okay. All right. We understood all these points. Now we need expressions for expressions of heat for different processes, like constant pressure, constant volume, constant temperature, like we did for the expressions of work. Okay. All right. Just give me a minute. Then we'll start. All right. Okay. Now let's come to the expressions part. Expression of heat. For different processes. So let's come to the first one, that is, and it's for closed system. Okay, for the closed system. Right here. The first one is constant volume, which is isochoric process. So we know that for we can apply the above equation. Sorry. Del Q is equal to du plus PdV. Just know we got to know from this equation. So we know that for a constant volume, this part is 0. Change in volume is 0. So del Q is nothing but du. And you know that it is mCV delta T. So CV is constant volume specific heat. All right, which is nothing but equal to du. So du is mCV dt. Or you say it as mCV dt only. Okay, mCV dt. So this equation is applicable for all the processes because it contains all the properties in it. And properties are point function. Properties are point function. Okay. So in this equation is valid for reversible process, but PDV is 0. That's why it can be applied for any kind of process, but for a closed system. Okay, because it contains all the properties. It doesn't depend on the path. So efficiency will be maximum because it's between the 2 points. It doesn't depend on which point to which point what path you are taking from which point, from 1 point to 2 point to reach. Okay. So this equation is applicable for all processes, because it contains all properties and properties are point function. Right. Also, this is an internal energy and it is a function of temperature if you see coming only for ideal gas. Okay. So this internal energy du, internal energy is function of temperature only for ideal gas. Okay. Now coming to the concept of enthalpy in this. What do we understand by the term enthalpy? What is enthalpy? It is nothing but how much amount of energy is associated with a flowing fluid. If a fluid is flowing, then how much energy it is carrying along with it. So it basically represents the total heat content of that system. Whatever your system is, it represents how much is the total heat content inside that system. Okay. It represents the total heat content of system, or you can say amount of energy associated with flowing fluid. Right? How can you write? The enthalpy is H, symbol is H, is the internal energy plus PV, P into V. Okay. Internal energy plus PV. This is your enthalpy. The representation for that. Now, what is specific enthalpy in it? Specific enthalpy is nothing but summation of specific internal energy plus flow work. It is a summation of specific internal energy and flow work. I'll explain what's flow work. Let me write. So it will specific enthalpy will be represented with small h. Okay, it's nothing but capital H by mass. Enthalpy per unit mass. It's nothing but capital U by mass plus capital P by V by M. Okay. So small h is equal to small u plus capital P small v. So specific volume. Okay. And this is this small v specific volume, and this PV is the flow work. Let me use this. This is your flow work. And this small v is your specific volume. All right. This is your specific enthalpy. And this is your specific internal energy. Somehow specific internal energy and flow work. All right. What is the flow work? Capital P small v in the terms of representation. What flow work, or you can say it's a displacement work. It is nothing but an amount of work required to display infinitely small fluid element into or out of a control volume. Okay. Suppose, let me write first. Flow work, or you can say displacement work. If you have a control volume, okay. So from here, some fluid is entering, and from here, fluid is exiting out. Okay. And you take a very small element in it. Okay. As well as at exit as well. Okay. So this is a very small, having a small dA dx. Okay. And this is a control surface. So this is a control surface. So suppose your fluid is flowing. Okay. You assume in that fluid flow some small volume inside that, and you make a boundary outside that volume. So that is your closed surface. Whatever fluid is flowing inside this is a control volume. So what fluid enter inside that control volume? So it's very infinitely small element. This element is a very infinitely small element. Okay, very infinitely small element. How much amount of work is required to displace this small fluid element from into or out of the control volume? Inside the control volume or outside the control volume? How much amount is required? That is your flow work. Okay. So this whole is a control volume. Surrounded by a control surface, and you assume small fluid element. Okay. How much amount of work is required to displace that small fluid element? Okay. Okay. So I'll write this amount of work required to displace infinitely small fluid element. This is your small fluid element. Into or out of out from control volume. Okay, from a control volume. So what is a control mass? There are two definitions comes here. What is a control mass? What is a control volume? Let me write. Let me make a short table. It says that control mass, control volume and here is mass interaction and energy interaction. So in a control mass, you know that you are not exchanging the mass. So there is no mass exchange, but only energy exchange is happening. Whereas in a control volume, here the fluid element mass is also exchanging as well as it is taking some energy. So both are there. Mass exchange and energy exchange is happening. So where only energy interaction happens, that is nothing but a closed system. Okay. So this control mass behaves as a closed system. Whereas when mass as well as energy interaction takes place, it behaves as an open system. All right. So control volume is also known as open system, and boundary of control volume is also known as control surface. This boundary. Control volume is also known as open system from here, whereas boundary of the control volume is the control surface. Okay. Whereas control mass is also known as closed system, which we wrote here. So I'll write this point also. Control volume is also known as open system. And boundary of control volume is also known as control surface. Okay, control volume, control surface, and control mass is also known as system. Closed system. Okay, control mass. So we started with the definition of enthalpy, which is U plus PV. Then we came to a specific enthalpy, which is enthalpy per unit mass and summation of specific internal energy plus flow work. Where flow work is nothing but if you the amount of work required to displace a small fluid element into or out from the control volume. What is a control volume? It's a volume which is inside a fluid flow. Okay, imaginary kind of volume which you assume, which is surrounded by a control surface, and there is a fluid element which is taking some mass, which has some mass and some energy. The amount of work which is required to displace that small fluid element is the flow work. Control volume is also known as where mass interaction as well as energy interaction happens, which is nothing but an open system. Control mass is nothing but where you are controlling a mass interaction. No mass interaction is happening, but energy interaction is happening. So that kind of system is a closed system. Okay. All right. Pretty much clear now in whole. Now come to the second process. We are done with the constant volume process. Let's come to the constant pressure process. pressure is constant. That is isobaric process. So we know that equation is so if pressure is constant, this P can be taken inside a derivative. So this will be d of PV. And both are derivatives now. So you can write it as derivative of U plus PV. And you know that this U plus PV is nothing but enthalpy dH. Okay. And you know that since del Q is mCp dt, okay, mCp delta T at constant pressure, specific enthalpy at constant pressure. Therefore, dH is nothing but mCp dt. Okay. And this above equation is again valid for all the processes because it contains all the properties, and properties are point function. And also again, H is a function of temperature only for ideal gas. Function of temperature only for ideal gas. I'll write again these 2 points. Above equation. Right. Let's write like this. Applicable for all processes. Because it contains all properties and properties are point function. Also, enthalpy is a function of temperature. H is a function of temperature only for ideal gas. All right. So constant pressure process is also completed. Now you know why enthalpy concept come after the constant volume process we have to introduce, so that you can write it in this form. Okay. Now third process is constant temperature isothermal process. Temperature is constant. Okay. So again, you know that del Q is du plus PdV. Okay. Since temperature is constant, that means dT is 0, change in temperature is 0. All right. And you know that du is nothing but mCv dt. You know that du is internal energy at constant volume process. Okay, it's a constant volume process. So dt is 0 here. So therefore, your net heat interaction. So that means your du is also 0. So therefore, del Q is nothing but del of work. Or instead of writing this, you write it in the form of del of W. Is nothing but del of W. And we know that what is the work expression for a isothermal process for a closed system. We very well know. Either it's an open system or a closed system, both the works come out to be same. It is nothing but C ln V final by V initial. In the previous tutorial only we derived this, or C ln P initial by P final. Okay, you can check the notes of the previous tutorial. So this is your expression for constant temperature. So for isothermal process, heat as well as work are same. Now coming to the next process, that is adiabatic process. Fourth, adiabatic process, where there is no heat interaction between system and surroundings. We know that. So if there is no heat interaction between system and surroundings, what happens? dq is 0 in that scenario. So heat expression is 0 itself. So del q, there is no expression of heat. Del q is 0. And we are finding out expressions for heat only. All right. Next is the concept where relation between Cp, Cv, R and gamma is required. Let me write. Cp, Cv, R and gamma. So we know that adiabatic index Cp, gamma is Cp by Cv. Cp by Cv. So this implies Cp is nothing but gamma times Cv. Also we know that Cp minus Cv is nothing but R. So put this Cp here. Gamma times Cv minus Cv is equal to R. Take out Cv common, gamma minus 1 is equal to R. So therefore, Cv is R over gamma minus 1. And put this Cv back here. Therefore, Cp is gamma times R over gamma minus 1. So these are the relation of Cp, Cv, R and gamma. Very important relations. Now using these relations, we'll come to the polytropic process. PV raised to power k is equal to constant. Okay. Or PV raised to power n is equal to constant, whatever. The fifth process is polytropic. Polytropic process. Now let's rewrite for this. So again, del Q is du plus del W. We know that what is a work expression for a polytropic process from the previous class, previous tutorial. That is Pi Vi minus Pa final V final upon n minus 1. Okay. So polytropic process was PV raised to power n is equal to constant. And du, you know that it is mCv dt. And work for a polytropic process is Pi Vi minus P final V final over n minus 1. Cv you can write it as R upon gamma minus 1 from here. Cv here you can write it as m into R upon gamma minus 1 into dt. dt is nothing but, all right, let's first write. So this expression will be as it is. And dt can be written as T final minus T initial upon gamma minus 1 plus P initial, this expression as it is above. You know that MRT is nothing but PV, ideal gas law. It will be P final V final minus P initial V initial. So the first MRT is P final V final, second MRT is P initial V initial upon gamma minus 1 plus the term from above is P initial V initial minus P final V final upon what? Why? What it should be? N minus 1. Okay. All right. Now you take out P initial, P final, V final out of it. So P final, V final minus P initial, V initial. You take this out common. So this first term will be 1 upon gamma minus 1 from here. And here it will be minus sign should be there. And it will be 1 upon n minus 1. All right. So if you take the LCM common factor, so it is P final, V final minus, sorry. If you manipulate the terms and solve it, it will be P initial, V initial minus P final, V final upon n minus 1 into gamma minus n upon gamma minus 1. Okay. And this term is nothing but your work done for closed. This term is work done for closed. So heat interaction is work done of closed times gamma minus n upon gamma minus 1. All right. And if you can also verify that if the process becomes adiabatics, then your n will be gamma. So this will be gamma minus 1 gamma. So this is 0. So del Q comes out to be 0 only. Okay. So our expression is very well right. Okay. And if I'll write here, if n is equal to gamma, if adiabatic process, then n is equal to gamma, therefore del Q comes out to be 0. All right. We are done with all the 5 processes: constant volume, constant pressure, constant temperature, adiabatic, and polytropic. Expression for all the heat interactions. Okay. Now we understood what is specific heat for constant volume and constant pressure. If I ask you what is specific heat for polytropic, what is polytropic specific heat? How we can get that? So we'll prove that. Just give me a minute. All right. So let's come to the polytropic specific heat. What is a polytropic specific heat? How to get the expression for that? So we know that from the above expression, since del Q is work of closed times gamma minus n over gamma minus 1. Okay. And what is work of close? So write gamma minus n over gamma minus 1. Work of close is mRT initial minus mRT final over n minus 1. Take out the mR common. Gamma minus n upon gamma minus 1. T initial minus T final over n minus 1. Now what you do, you write these three, this 3 together in the sense that, and take out m outside, r upon gamma minus 1 into gamma minus n upon n minus 1 into T initial minus T final. Okay, it's the same only. So m is here, r over gamma minus 1 is here, gamma minus n upon n minus 1 is here. Okay. All right. Now we know that r over gamma minus 1 is nothing but Cv. So m into Cv. And if you take minus sign common out of it, and minus sign common out of it, that will become plus only. So this can be n minus gamma upon n minus 1 into T final minus T initial. Okay. T final minus T initial. Now, mCv n minus gamma upon n minus 1 into T final minus T initial. All right. Any doubts still here? So mCv delta T is nothing but your heat, and C there is nothing but your, for a polytropic process, is this. Okay. So this was your del Q. So Cp V, the power of n is equal to constant process, that is a polytropic, is nothing but Cv times n minus gamma upon n minus 1. This is your final expression. This is your polytropic specific heat. Okay, polytropic. This is constant Liouville specific heat times n minus gamma upon n minus 1. And always see that value of a polytropic specific heat is negative, because this numerator will always be negative, since gamma is greater than n greater than 1. So this is a n minus gamma. So this value will always be negative. Okay. So I'll write this point. Value of polytropic specific heat that is this. Is negative if gamma is greater than n is greater than 1. Okay. Now let's come do some few proofs. Let's do. Okay. Very important proofs. First proof. We need to prove that value of value of heat interaction is 0 for adiabatic process. You have to prove that thing. We just wrote that heat interaction is zero. How we will prove it? Prove that value of heat interaction is zero for adiabatic process. So we know that del Q is du plus del W. Okay. What is du? mCv dt. Okay. And what is del W for a adiabatic process? We know that it's P initial, V initial minus P final, V final upon gamma minus 1. Upon gamma minus 1. We know that. You can write CV as R over gamma minus 1, M R over gamma minus 1, and dt as T final minus T initial plus P initial, V initial minus P final, V final over gamma minus 1. Okay. Now MRT can be written as from the Arrhenius law PV. So it will be P final, V final minus P initial, V initial over gamma minus 1 plus P initial, V initial minus P final, V final over gamma minus 1. So this and this cancels out, this and this cancels out, which is nothing but because both have same common denominator. So therefore, heat interaction for adiabatic process is zero. Value of heat interaction is zero for the adiabatic process. Hence, proved. Okay, clear? Okay. Now let's come to, we have to prove PV raised to power gamma is equal to constant for reversible adiabatic process executed by the gas. Prove PV raised to power gamma is equal to constant works for reversible adiabatic process executed by gas. Take a minute or two and think that how you will prove. Think about this. All right. I hope you might have done so far. So let's prove. So we know that for reversible adiabatic del Q is 0. Just now we proved for adiabatic process. This is this. Okay. So since del Q is du plus pdv, so this is 0. Therefore, du plus pdv is 0. Okay. So du is nothing but negative of pdv. Okay. And du is m dv dt is equal to minus pdv. This is your equation 1. Let us suppose. This is your equation 1. Now, another way, from enthalpy H is equal to U plus PV. So DH will be what? DH is taking the differentiation on both the sides. Du plus, let me write it like this, on differentiating. Both sides. DH is du plus d times of PV, which is du plus P dV as per the chain rule, and V dP. Okay, that is DH. And you know that this is dq only, del q only. Okay, so DH is del q plus VDP. Okay, del q plus VDP. So therefore, del q is DH minus VDP. If you take this, rearrange it. Okay, very important equation. This is very important equation. The del q is DH minus VDP. But now we are dealing with the adiabatic process. Since del q is 0, therefore DH minus VDP is 0. So DH is equal to VDP, and DH is nothing but MCP dt, which is equal to VDP. This is our equation number 2. Now what you do, divide the equation number 2 by equation 1. Divide equation 2 by 1. So what was your equation 2? MCP dt is equal to VDP. And what was your equation 1? MCV dt is equal to minus PdV. MCV dt minus PdV. Okay, this PdV. So M cancels out, dt cancels out. So you are left out with Cp by Cv minus time VdP upon PdV. And Cp by Cv is gamma. Okay, so gamma is equal to minus VdP upon PdV. Transpose. So gamma times dV by V is plus, let us say, equal to minus dP by P. Okay, you can write this. Take it on the left hand side. It's gamma times dV by V plus dP by P is equal to 0. Now you integrate both the sides. Integrating. This is ln of V plus ln of P, right? Gamma times dV by V to the power of gamma, sorry. You can write like this, okay? Is equal to 0. Is equal to constant, sorry. integration of 0 is constant. So multiply PV is equal to PV raised by gamma is equal to constant, because ln of constant is constant. So hence it is proved. Hence that PV raised by gamma is equal to constant is working for a reversible adiabatic process which is executed by the gas. Okay. Pretty easy. Now let's come to proof of Mayer's equation. What is a Mayer's equation? Mayer's equation is Cp minus Cv is equal to R. You have to prove this. It's just a minute of. Take a minute. Okay. Pretty much simple equation again. We know that proof. Let's do. We know that H enthalpy is nothing but U plus PV. Okay. Differentiate. You will get dH is equal to du plus d of PV du, and PV you can write it as MRT. Now dH is nothing but MCP dt, and du is nothing but MCV dt, and it can be written as MR outside constant MR dt. Okay, so M dt cancels out on all the sides. Okay, therefore Cp is equal to Cv plus R. Therefore Cp minus Cv is equal to R. Hence proved. Pretty much easy, right? Now next thing, you need to prove that T final over T initial is equal to P final over P initial, the power of gamma minus 1 by gamma, is equal to V initial by V final gamma minus 1 for reversible adiabatic process executed by gas. for reversible adiabatic process executed by prove this. Again, it's a very simple proof. Try this out. Okay, let's do the proof. So just now we proved that PV raised by gamma is equal to constant for reversible adiabatic process. Okay, so that means P final V final is equal to the power of gamma is equal to P initial V initial to the power of gamma. Okay, since we know that from the ideal gas law, PV is equal to MRT. Okay, put this V as T, therefore V is nothing but constant, sorry, T by P. Okay, now put this V in any of them. Therefore, P final, or you can say, should not put here. We should put this here. Therefore, P T over P power gamma is equal to constant C. Okay. So it will be P to the power of gamma, P to the power of 1 into P to the power of minus gamma is equal to constant. So T to the power of gamma, P to the power of 1 minus gamma is equal to constant. Correct? So you can write it as T final, P final is equal to T initial gamma, P initial 1 minus gamma. So T final by T initial to the power of gamma is equal to P initial P final to the power of 1 minus gamma. Okay, correct? Just took on both the right side. So it can be written as T final by T initial. And if you change the sign here, so final will come on the up numerator. So this is P final by P initial to the power of gamma minus 1, and this gamma goes on the downside. So that was the first part. T final by T initial is equal to P final by P initial to the power of gamma minus 1 by gamma. Okay, hence proved. Hence, now the next part. Since we know that PV raised by gamma is equal to constant, so write pressure in terms of volume this time. T by V, V to the power of gamma is equal to constant. So again, it is the same thing. T to the power of V power gamma minus 1 is equal to constant. So T final, V final, gamma minus 1 is equal to T initial, P initial, gamma minus 1. Transpose it, T final by T initial is equal to V initial by V final to the power of gamma minus 1. That was the third thing. T final by T initial should be equal to V initial by V final to the power of gamma minus 1. Hence proved. Hence proved. Okay. All right. Now we are done with these proofs. Now, what are the important points regarding heat and work? That's right. Important points. Regarding heat and work. So the first point is both are path function, both are inexact differential, both are boundary phenomena, and both are energy in transit or transient process. Okay, that means as the heat and work travels along the path, energy flows in the motion. Okay, let me write. Both are path function, both are inexact differential, both are boundary phenomena, and both are energy in transit. Or you say transient phenomena. What does it mean? That is, as heat and work travels along the path, then energy is in flow, or you can say energy is in motion. This implies in flow or motion. Okay. Now, what are differences between both of them? Heat and work. Differences. So all the forms of energy interactions are work interactions, except energy interaction is due to the temperature difference. First difference was this, as per the definition. And area under the pressure volume plot gives you nothing but work interaction, whereas area under the temperature entropy plot gives you heat interaction. We'll come with that entropy and everything. Just we are writing a differences. Okay. In the coming tutorials, we'll come across with the entropy as well. So all forms of energy interaction are work interaction, except energy interaction due to temperature difference, then area under the PV plot, PV mean pressure volume plot, provides work interaction, whereas area under temperature entropy plot provides heat interaction. Okay. All right. Well, all the work producing, some important points I'm telling, all the work producing devices are shown in clockwise direction on pressure volume and temperature entropy plots, whereas all work absorbing devices are shown in anti-clockwise direction. Okay. Note all work producing devices are shown in clockwise direction on pressure volume and temperature entropy curves, whereas all work absorbing devices are shown in anti-clockwise direction on pressure volume and temperature entropy curves. What are work producing are like in the IC engines. Engines are the work producing devices like Otto cycle is there, Rankine cycle is there, Carnot cycle is there. So what is a work producing? Otto cycle, Rankine cycle, or Carnot cycle. Whereas work absorbing devices are your refrigerator, air conditioners. It's a reverse Carnot cycle or VCRS, vapor compression refrigeration systems. Reverse Carnot cycle, or you say VCRS. Okay, you'll study in your power plant, IC engines, or refrigeration subjects. Okay. Next point to note is whenever there is a battery, there is only work transfer. There is no heat transfer. Okay. Why? What happens when you are charging the battery? Work is done on the system. You are providing the electricity to your system. Whereas when it is discharging, work is done by the system. How the work is done? Because the flow of electrons takes place in a given direction. Okay. So there is a displacement of the electrons. So work is done on the system during charging, whereas during discharging, work is done by the system. So phone battery, okay, or any other household batteries are the example. So whenever there is a battery, there is only work transfer. No heat transfer take place. Example, phone battery. So during charging, what happens? Work is done on system, done on it. And during discharging, work is done by it. Okay, how? Because by flow of electrons in a given direction. All right, there is a flow of electrons. There is no heat produced. Work is done. Okay? There is no temperature difference happening. Now, also one important point is density of water is maximum at 4 degrees Celsius, and on decreasing the temperature, it will expand. So then what will happen? Density will decrease. Volume is expanding, water is expanding. So density will decrease. And from the slope of the fusion curve also, you can see that it is negative exceptional for water in the case of water. Okay. The next point to notice, density, of water is maximum at 4 degrees Celsius, and on decreasing its temperature, it will expand. Water will expand. Okay. Next point. Triple point. We know that what is a triple point, where all the phase exist together, solid, liquid, gas. For a water, triple point is a point on the PT curve, on pressure temperature curve, whereas it is a line on PVT curve, on PV curve, sorry, PV curve, or surface on PVT curve, right? It's a point on PT, point, PT point, okay? You can remember like that, line on PV curve and surface on PVT curve. Okay. So PT curve, if I draw, and triangle on UV curve, another that, and triangle on internal energy versus volume. Okay, so if I draw a PT curve, pressure temperature, so it looks like a point. So this is your point. This is your triple point. Okay, so here it is solid. Here it is liquid, and here it is gas. So this point is your triple point. Triple point is a point on PT curve. Okay. Anyways, so let's wrap up for today's lecture, and you will get your all these notes and this tutorial recording on my YouTube channel, as well as you enroll in the NPTEL course, you will get the Excel sheet where you will see all the links for the every tutorial, as well as the link for this drive where I have uploaded all the week lectures, PDFs. Okay. Even if you're not enrolled in the course, you are watching it for the first time on the YouTube. So my YouTube channel is NPTEL with Varnit. Okay, so you can check it out. In the group description of the video, I will put the link of the sheet where all the tutorial videos as well as the Google Drive link is there for the PDF of these notes. Okay, I hope there are no doubts remaining, and I expect that you are continuous and regular with the lectures and your assignments. And I'll see you in the next week, same time, Tuesday, 6 to 8 p.m. for week 4. Okay, let's end the tutorial. Thank you for joining.